Start this up and go. It might be on the left-hand side. Do you find it?
It's a new platform.
I know. It looks so different. And for some reason, like on my end, there's way more steps to do now for some stuff. So I'm like, what was the point of that? Because there used to be a lot of steps anyways. But
I did a lot better.
yeah, it was a lot. It was a lot better. That's nice.
I forgot to use words.
I know you told me it was going to be a bad one, but it's not as bad as you think. I'm pretty sure. Okay. You're like, that doesn't help me. Yeah. All right. No review, nothing, I guess. We just had the test on everything that we covered. So we'll just start 3.5. So 3.5 is on implicit differentiation. So the test that we just had was on kind of the major tools that we'll have for just finding derivatives, right, which is differentiating an equation or a function. And so, but so far we've only dealt with functions that have the form of y equals blah, blah, blah in terms of x, right? And so, but we know that there are functions like x squared plus y squared equals 25, for example. That's a circle where we could solve for y, right? But x and y, right, are just kind of baked into the same thing, right? And so then we have an implicit function. So far, all our functions have been in the form, or could easily be arranged to the form, or can easily be rearranged to the form of one variable, right, usually y, expressed in terms of another variable, usually x, expressed in terms of another variable, x. Things like y equals the square root of x to the 3 plus 1, or something like y equals x sine x, right? We've seen all these functions where we've got y on one side and x is on the other side, right? And so here, y is explicitly defined in terms of x. We're saying, hey, y equals this thing. Some functions, however, are defined implicitly, by a relation between x and y, by a relation between x and y. such as something like x squared plus y squared equals 25. That would be a circle with a radius of 5. Or something like x to the 3 plus y to the 3 equals 6xy. It's not important, but this is called the Folium of Descartes. And this is a circle with radius 5. So a lot of these implicit functions are, we need them because they make up these nice shapes or kind of patterns or whatever. And so here, right, in both of these situations, y is implicitly defined in terms of x. Y is implicitly defined in terms of x. Right? Because especially in the second one, right? In the first one, sure, we could rearrange, right, and find that y is the plus or the minus of the square root of 25 minus x squared. That's fine. Sometimes we don't want to do that though, right? Because we get that split of plus and minus. So the upper and the lower half of the circle. Right? A little bit trickier to solve for y in something like the second one, right? We've got x to the 3 plus y to the 3 equals 6xy, right? Very tricky to pull that y out and solve for y explicitly, but because we don't need to, because we have implicit differentiation, right? We can just leave them as implicit functions. And in Maple, you'll see there's an implicit diff command that'll just do it for you. Right? And so today we're going to do implicit differentiation. So when functions are defined implicitly, we can use implicit differentiation. We can use implicit differentiation to find the derivative of y. So how does it work? Implicit differentiation says that we differentiate, surprise, both sides of the equation with respect to x. So differentiate both sides of the equation with respect to WRT, which I guess I'll do it backwards, with respect to, but I'll use that a lot, right? WRT with respect to x. And that's our first step. The key is to remember that y equals f of x, right? So y is a function of x. And so that means that we're going to have a chain rule, right? Because if you've got y in there, then, and you're looking at y squared, for example, then that's f of x squared, which means you have to take the derivative of the outside and multiply it by the derivative of the inside. So it's going to look a little bit weird, but I think as long as you kind of tell yourself that when you're taking the derivative of y, you just take it normally, right, in terms of the chain rule, and then you multiply it by the derivative of y. And that's just how it's going to go. And that's the only trick with implicit differentiation. So if you remember that y equals f of x, this means that we need the chain rule. And then solve for dy dx, right? Or simply y prime, depending on which notation we're using or that you prefer to use. I don't find that this blurb tells me exactly what I need to do, right? But once we do a couple of examples, you'll start to see the pattern of how we deal with that y. And then it's not going to be any different, right? We can still apply, or we need to still use the product rule, the chain rule, the quotient rule, all those rules that we've worked on already. So let's do an example. We'll start nice and slow. If x squared plus y squared equals 25, find dy dx. So find the derivative of y in terms of x. And then, remember that the derivative is the slope of the tangent line, right? And so we're developing a function for the slope of the tangent line. And so then what we're often going to be doing is find an equation of the tangent line to the circle x squared plus y squared equals 25 at the point 3, 4. So first off, this is our first stab at implicit differentiation, right? But here we go. So we want to find d dx of x squared plus y squared, right? Because our very vague outline of things that we needed to do was just to find the derivative, so differentiate both sides. So we can set that up here, d dx of 25. Since I'm adding inside the brackets on the left-hand side, right, I can just bring that derivative inside. So then I'm taking d dx of x squared plus d dx of y squared equals, and then the derivative of 25 is just 0. The derivative of a constant, because there's no x in there. The derivative of x squared with respect to x, that's fine. That's just going to be 2x. Right? So that part we can handle. So we'll do 2x plus, and then here, this is the new part. It's the only new thing that we have to deal with. So this becomes d dy of y squared times dy dx. Because, right, we've got this y squared, which is essentially f of x squared. If you think about the chain rule, right, we have to take the derivative of the outside and then multiply it by the derivative of the inside. And so On the outside, we've got that square. So then we're taking the derivative with respect to y of y squared. And then we're multiplying by the derivative of the inside, which is just dy dx. And then later on, what we'll do is we'll just replace that with y prime, right, to make it look a little bit easier. But we're doing the same thing. So this little section, right, or maybe what I'll do, I'll put it in 2 steps. Equals 0. So I've got 2x plus, and then the derivative of y squared with respect to y is just going to be 2y plus times dy dx. So whatever the derivative of y is with respect to x, you could replace that with y prime equals 0. So now, if we go back to our instructions here, differentiate both sides of the equation with respect to x. So that's what we've done, right? We boiled down both sides, took a little bit of extra care with the y, right? Because it's basically a chain rule. And then we solved for dy dx, and dy dx you could just easily replace with y prime, and that's allowed. And we will be doing that. It's just to start off with, we use the dy dx. So if we solve for dy dx, so now we can solve for dy dx. So I get 2y dy dx is negative 2x. So dy dx is negative 2x over 2y, which puts dy dx at negative x over y. We did it. So this, right, this is the derivative. This is the derivative. Oops. Oh, eraser. Derivative of y with respect to x. Yeah. Is that good? And the derivative is a function for the slope of the tangent line at any value of x and y. Which I guess I can add. The slope of the tangent line at xy. So if we need to find the equation of a tangent line, right, the first thing that we're going to need is, well, we need to know the point that we're interested in, right? But that would be given. And then the next thing that we would need to do is to find the slope of this tangent line at that point. And so part B, at the point, and we were given at the point 3, 4, we know that dy dx is negative x over y, which is going to be negative 3 over 4. Dy dx. So this is the slope of the tangent line at 3, 4. if we know a point and we know a slope, we can use the point slope form of a line. The point slope form of a line y minus y naught equals m times x minus x naught, right? Where x naught at x naught y naught. That's the point that you know. So therefore, an equation of the tangent line to the circle at 3, 4 is y minus y naught equals m times x minus x naught. Y minus 4 is the y value that I know, is negative 3 over 4 times x minus 3 is the x value that I know. Now it's just down to algebra, right? And so we can bring the negative 3 over 4 inside. However you want to do it is fine. Negative 3x over 4 plus 9 over 4. Y equals negative 3x over 4 plus 9 over 4 plus 4. I'm going to cheat and put it on the same line, right? Because I'm dealing with fractions, so I want to have a common denominator. And so I'm going to multiply this by 4 over 4 to get it over 4. And then I have y equals negative 3x over 4. And then plus 9 plus 16, 25 over 4. Y equals negative 3x plus 25 all over 4, which means I can bring that 4 over if I want to, right? You can leave it in this form or even in the previous form if you want it in the form of y equals mx plus b for a line, right? Or what we can do is we can redefine it as an implicit function, right? Bring it back to an implicit function. And so we can bring the 4 over, so we get 4y is negative 3x plus 25. And so we get 3x plus 4y equals 25. We can bring it back to an implicit function. Oh. If we want to. Negative 3x over 4 plus 25 over 4 works too. Any questions about that one? Let's do another one then. Example 2. Part A, we're going to find y prime if x to the 3 plus y to the 3 equals 6xy. Y prime, right, is dy dx. And so it's the exact same thing. I'm just using more or different notation. But in general, the y prime notation just looks a little bit cleaner often. And so that's usually the one that I'm going to go with. It just depends. Part B, find the tangent to the Folium of Descartes. Tangent to the Folium of Descartes. X to the 3 plus y to the 3 equals 6xy at the point 3, 3. Part C, we'll add another part here. And maybe I'll scoot this also, it's on the same page here. Part C, at what point in the first quadrant is the tangent line horizontal? At what point in the first quadrant is the tangent line horizontal? So then we're going to take it one step further and say, okay, well, if the tangent line's horizontal, right, it means that the slope has to be 0, which means the derivative must be 0. I'm pretty sure that you do this in the lab, either as a lab problem that you're working on in the implicit diff lab, or it might even be on the lab exam where you have to use the implicit diff and you have to find the equation of the tangent line and just kind of go from there, right? So I think, I'm not 100% sure, but because it's been a while since I taught Calc 1 lab. Anyways. All right, so for part A, if we just write out our function x to the 3 plus y to the 3 equals 6xy, if I have to differentiate this, with respect to x, then, well, all the x's get treated the same, right? And the only key thing here is that I've got an x times y. So here I'm going to need to use the product rule. So what we get is we get 3x squared. X to the 3 is just 3x squared. And then for the y to the power of 3, right, remember to think of y as f of x. So then you have f of x to the power of 3, which means you have to do the chain rule, right? And so what it's going to look like is 3y squared, and then times the derivative of y, which from now on we'll just write as y prime, right? So whenever you take the derivative of the y, right, you just follow it up with a little y prime on the outside. Or if you've just got a y, right, then the derivative of that y is just y prime. And so here, if we've got the product rule, we've got 6x times y, let's say. Right? And so depending on which way you want to do it, if you like fg prime plus gf prime, or the opposite of that, I was seeing both in the test. So, and it really doesn't matter the order that you do. So if we call this part f and this part g, and you could have put the 6 on the y, it doesn't matter. Then we get, and if we do fg prime, let's see, let's write this down. Fg prime plus gf prime then leaving f alone, we get 6x, and then the derivative of y is just y prime, oops, plus y is left alone times the derivative of 6x with respect to x is just 6. So I'm going to actually write 6y to make it look a little bit better. Cool. So now we've taken the derivative, and now we need to solve for y prime, right? But when we've got the prime notation, it's just easier to see, right? We can rearrange. And so I'm going to bring all the y primes over to one side and then slowly shift everything else over to solve for y prime. And so now I can solve for y prime. So I get, oops, I get 3y squared y prime minus 6xy prime is 6y minus 3x squared. Pulling out a common y prime, I get y prime times 3y squared minus 6x is 6y minus 3x squared. I wonder if it'll fall out. In my notes, I've simplified up here, but way earlier on. Because see up here in the, I've got common 3s and common 6s, which I can kind of deal with early on, which I didn't do. So I'm curious, we'll see if it falls out. Doesn't really matter. Right, because I could have pulled out a common 3 and pulled out the common 6 and just been left with 2, right, on the left-hand side, and no coefficients on the right-hand side and the left-hand side. Anyways, we'll see if they fall out. So now I've got y prime is 6y minus 3x squared over 3y squared minus 6x. Yeah, can probably just pull out a common 3 on both of these. So y prime is 3 times y minus, 2y minus x squared over 3 times y squared minus 2x. These 3's I can cancel. And so I'm left with y prime is 2y minus x squared over y squared minus 2x. So now I've got a function for the slope of the tangent line. So now I want to find the equation of the tangent line at the point 3, 3. So at 3, 3, y prime is, well, let's just refresh our memories here, 2y minus x squared over y squared minus 2x. 2 times 3 minus 3 squared over 3 squared minus 2 times 3 puts me at 6 minus 9 over 9 minus 6. -3/3, -1. What's this that we just found? This is the slope of the tangent line at 3, 3. Let me see if we can use Desmos, but I'll just steal the Folium of Descartes picture here. Maybe it was way back. Here it is. So the Folium of Descartes, it's not a circle, it's a, I don't know. So at 3, 3, right? The slope here looks like it might be -1. That makes sense, right? And that's what we found. So the equation for the tangent line now, right? Again, we're going to use the point slope form of the line. And so therefore, an equation of the tangent is y minus y naught equals m times x minus x naught. Y minus 3 equals -1 times x minus 3. So I get y minus 3 is -x plus 3. So y is going to be -x plus 6. Right? Or implicitly, x plus y equals 6. It doesn't matter which way you write it. I'm okay if you stop at just y equals -x plus 6. But if we start with an implicit function, we just kind of like to finish on an implicit function. So we just rearrange it, because then it'll be easier to see patterns if there are any, right? And so that's why we're rewriting it. But like I said, if you leave it at y equals -x plus 6, that's fine. So we found the equation of the tangent line. And now part C says we want to find at what point in Q1, the first quadrant, is the tangent line horizontal? Right. We have to remember that it's horizontal means that the slope is 0, which means y prime must be 0. So if we go back and we look at y prime, well, y prime is 2y minus x squared over y squared minus 2x. Oh, minus. So we want to force this to be 0. The denominator can do nothing about it, right? It can never be 0. We can't divide by 0. And so the only thing that can make this thing 0 is if 2y minus x squared is 0. Right? So y prime will only be 0 if 2y minus x squared equals 0. Right? As long as that doesn't make y squared minus 2x 0 as well, right? Because then we're dividing by 0 and that's illegal. So provided that y squared minus 2x does not equal 0, right? Whatever value of x and y we find, we have to check that y squared minus 2x doesn't equal 0. So if we zoom in on the numerator, right, 2y minus x squared, and we force it to be 0, then we can solve for y and figure out, well, what y is in terms of x at the point where the slope is 0. So in general, so if we have 2y minus x squared equals 0, then we have 2y equals x squared. So then y must be x squared over 2. This is the point where 2y minus x squared equals 0, which means we have a horizontal tangent. You could have easily, or just as easily, solved for x, but usually we like to solve for y, right? That's just how we typically work, right? And so now if we think about, okay, so this point has to be in this original equation, right? Because it has to be on this little loop-de-loop, right, in the first quadrant. And so the point that we're interested in, the point that we are interested in must be on x to the 3 plus y to the 3 equals 6xy, right? Otherwise, it can't be a tangent. I'll even say that. Otherwise, it can't be a tangent. So we know the point of y that satisfies that the slope is 0. So now we can plug that into x to the 3 plus y to the 3 equals 6xy, right? Substitute y equals x squared over 2. And so now we can substitute y equals x squared over 2 into x to the 3 plus y to the 3 equals 6xy. So we get x to the 3 plus y to the 3, which is now going to be x squared over 2 to the 3 equals 6x times y, which is actually just going to be replaced with x squared over 2. If we simplify this a little bit, right, I get x to the 3 plus x to the power of 2 times 3 is x to the 6 over 2 to the power of 3 is 8. 6 divided by 2 is 3. And then x times x squared is x to the power of 3. I've got x to the power of 3 on the left-hand side and 3x to the power of 3 on the right-hand side. So I'm going to move those guys over together so I can collect like terms. So then I have x to the power of 6 over 8 is 3x to the 3 minus x to the 3. So then I have x to the power of 6 over 8 is 2x to the 3. So now I can multiply that 8 over, right, because it's the only thing that I'm bringing over. And so I get x to the power of 6 must be 16x to the power of 3. 2 times 8, because I've brought the 8 over. Yeah. Because we're trying to boil down for something for x, right? Because we plugged in the y. We could have easily just solved for x initially, plugged that in, and solved for y first. But because we like solving for y, and then we plug that in, all we have are x's, so now we can solve for x. And so as long as x is not 0, then we can divide that x to the 3 over, right? And we can say that x to the 6 over x to the 3 is equal to 16, which we can reduce to just x to the power of 3 is 16. Oops. And then finally solving for x, we get x is the third root of 16, or 16 to the power of 1 over 3, or roughly 2.5198, approximately. Got a little squished here. So now we know the value of x, where the slope of the tangent line is 0. So now we can find the value of y. So here, this is the value of x when y prime is 0, right? Which is the horizontal tangent. So we can solve for y at x equals 16 to the 1 over 3. It's probably the easiest. So we get y is x squared over 2. That's what we solved for. X is now going to be 16 to the 1 over 3, all to the power of 2 over 2. So we get 16 to the 2 over 3 over 2, which is roughly 3.1748. And we could probably simplify the exact answer a little bit more, but I think your calculator might do it for you. I think mine does. So therefore, the tangent is horizontal at the point where x is 16 to the 1 over 3 and y is 16 to the 2 over 3 over 2, or approximately, right, because it's easier to wrap our heads around approximate answers. 2.5198 and 3.1748. Any questions about that one? So we'll do another example. Give you guys a little bit of time to work on this one because it's just finding the derivative just for practice. So find y prime if sine of x plus y equals y squared cos x. Just the heads up though, right here, you're going to be using a chain rule. And here, you've got a product in a chain rule. So I'll give you guys some time to work on it. Leave this. Okay, so we write this out, right? We've got sine x plus y is y squared cos x. There's no way I'm going to be able to solve this thing for y, right? And so I have to use implicit differentiation. And so now, if I just kind of indicate that I'm differentiating here somehow, it's tough because you don't have an anchor, right? Like y prime equals this, because the equation's already there, right? And so, but if we have the chain rule, right, we've got sine on the outside and then x plus y on the inside. So then the derivative of sine is cosine evaluated at the inside. So the cosine of x plus y times the derivative of the inside. Well, that's just the sum of x plus y. The derivative of x is 1, and the derivative of y is y prime. That's the left-hand side done. Moving on to the right-hand side, we have to do the product rule first, right? And then for the y squared, we're going to have a chain rule. And so if we leave y squared alone and take the derivative of cos x, we get negative sine x, plus leave cos x alone, and the derivative of y squared, we've already seen, is 2y times y prime. So that's the derivative. Now we can simplify. So now, because I'm trying to solve for y prime, I'm going to try to get those kind of on the same side and then eventually shift everything else over and solve for y prime. Which means I need to shake it out of the 1 plus y prime times cos xy. So what I'm going to get is I've got cos x, actually I'll even write more of a note here, simplify to solve for y prime. So I get cos x plus y times 1 plus y prime times cos x plus y equals negative y squared sine x plus 2y y prime cos x. Just kind of rearranging things so that they're nicer to look at. Shifting the y prime terms over to the left-hand side and the non-y prime terms to the right-hand side, I get y prime cos x plus y minus 2y y prime cos x is negative y squared sine x minus cos x plus y. If you want to pull out the negative, you can, right? Just be careful. You don't have to. On the right-hand side, right, we could pull out a negative. But let's just leave it and focus on solving for y prime. So now I can pull out a common y prime times cos x plus y minus 2y cos x, which is negative y squared sine x minus cos x plus y. Oops. Solving for y prime, moving it over a bit so we can see, I get negative y squared sine x minus cos of x plus y over the cos of x plus y minus 2y cos x. And then we're done, right? All it said was to find y prime, and that's all we've done. How about another example? find y double prime if x to the fourth plus y to the fourth equals 16. So give you guys a little minute to do that, or at least to start finding the first derivative, and then we can get into the second derivative. So if we start with the first derivative, the first derivative, just making little notes here, would be 4x to the power of 3 plus 4y to the power of 3 times y prime. The derivative of 16 is 0. Solve for y prime. We get 4y to the 3y prime is negative 4x to the power of 3. So y prime, must be negative 4x to the 3 over 4y to the 3. 4's can cancel. So y prime must be negative x to the 3 over y to the 3. Now we've got another implicit differentiation here, right? Because we've got x to the 3 over y to the 3, and then it's negative. And we want to take the derivative of that again. So now the second derivative y double prime is going to be the derivative with respect to x of negative x to the 3 over y to the 3. I'm only using that differential operator d dx because I really don't want to see, don't do something like negative x to the 3 over y to the 3 prime. It just doesn't look good. And so we don't want to do that. And that's the only reason that we use the d dx instead. All right. This looks good. Does it work? Yes, but just looks better with the d dx. So now we've got a quotient rule there. Right? I guess you could make it a product rule if you wanted to, right? And you could bring the y to the negative 3 up top. But I'm just going to treat it as a quotient rule. And so what we have is that y double prime, and I'll need a lot of room here probably. Not a lot, but enough. So y double prime is going to be, and don't forget about that negative out front. It's going to be lingering this whole time. G, which is y to the 3. And then I want d dx of x to the 3, just to show what I'm doing here. But if you wanted to just do 3x squared, that's fine, right? If you wanted to just take the derivative of it, that's fine. But then minus f, which is x to the 3, times the derivative of g d dx of y to the 3 over, and I'll shift this negative down so it's way out in front, over y to the 3g squared, y to the 3 squared. So now I can simplify this. The only one that's going to be a little bit different or new, right, is that derivative of y to the 3, right? We get 3y squared times y prime. But that's the only new thing that we're dealing with here. So we've got negative y to the 3 times 3x squared, minus x to the 3 times 3y squared times y prime. All over y to the power of 6. 3 times 2. So this is all fine. We can probably rearrange some stuff, right? But the key here is that we know what y prime is, right? We don't want to have y double prime in terms of y prime, right? Because then all of a sudden we've got kind of 3 variables, right? X, y, and y prime. So, but we already know what y prime is because we had to find it originally. And so here, right, y prime, right, we know that y prime is what? Negative x to the 3 over y to the 3. So then we can replace that in there. And then we can simplify. And then we've found the second derivative. So now it's just a matter of some algebra here. So y to the 3 times 3x squared. Actually, I'll rearrange that a little bit. 3y, and I'll have my x's first. 3x squared y to the 3 minus 3x to the 3 y squared times negative x to the 3 over y to the 3, all over y to the 6. I'm going to pull that negative out, and then I'm going to collect my x to the 3 times x to the 3's, and I'm going to divide by y to the 3. And so I'm really focusing on that second term in the numerator. So I've got negative 3x squared y to the 3 plus 3x to the 3 plus 3 times y to the power of 2, I guess minus 3 technically, but might be easier to see it if it's all over y to the 3. Over y to the 6. Right. This y to the 2 is going to cancel, and I'm just left with a y in the denominator. To add the numerator, right, I need to get a common denominator. And so what I'm going to do is I'm going to have equals negative 3x squared y to the 3 times y over y plus 3x to the 6 over y, all over y to the 6. I'm just simplifying here, right? Nothing crazy. minus 3x squared y to the fourth all over y. And I'm going to just put it over the common y already. Plus 3x to the sixth over y to the sixth. Technically, y to the sixth over 1, right? I've got a fraction over a fraction. So now I can say, well, that's negative 3x squared y to the fourth plus 3x to the sixth over y, times 1 over y to the sixth. Y times y to the sixth is y to the seventh. And so I'm left with negative 3x squared y to the fourth plus 3x to the sixth over y to the seventh. Whew. But a lot of that was just simplifying, which we should be pretty good at by now. The trick was to substitute that y prime in. Yeah.
So when you have the y
Here?
squared over the 3x,
Uh-huh.
3 plus 3 y squared over y cubed.
Yeah.
When you do that, wouldn't that be over y to the negative 1 then? Because 2 minus 3 is negative 1, which then brings the y to the top.
Well, so what's going on here is technically we've got y to the 2 times y to the negative 3, right? And so then we get y to the power of 2 minus 3, which is y to the negative 1, which is why it's just y. So you get 1 over y, right? So you get 3x to the 6th times 1 over y, or y to the negative 1. And that's why it's still in the bottom. Right, because you always float it up to the top and make the denominator negative. I guess we could bring the 2 down. No, it gets weird.
It's just confusing because usually when you have like a quotient like that, 2 minus 3 negative 1. That's where I was confused.
Yeah. So it is negative 1, and that's why it's in the denominator. But it's y to the negative 1 up top, right? And so then I guess I skipped it's kind of here. I did it. Good. So there it is. Any questions about that one? Like I said, if you're finding the second derivative, the key is to remember that you already know the first derivative. So then you can plug it in and then simplify, right? So. How do we feel about some trig? What? Derivatives of inverse trig functions. It had to happen. More memorization coming your way. Derivatives of inverse trig functions. Trigonometric functions. We're going to look at how one of the derivatives of the inverse functions is derived, and then you can use the same method for the rest of them. But probably at the end of the day, you don't want to spend your time finding these derivatives anyways. You'll just probably have them memorized, and I'll give you a table just like I did before of the ones to memorize. But I'll show you how it works with arc sine or the inverse sine, right? And then you'll kind of know the deal. But at the end of the day, like I said, you'll probably just be memorizing this table, and that's it. Look at you. How lucky are you to be memorizing things? It's good to memorize things. It's like working a muscle. The more you memorize, the more you'll be able to memorize. And then the more you'll be able to memorize after that, but you have to work at it. Recall the definition of the arcsine function. Was y equals sine to the negative 1 of x. Which means that sine y equals x. Right? Because if the inverse sine is on the x, then I can move it over and wrap it around the y and just have sine. So sine of y is x, and that's just the definition of the arcsine, right? Or the inverse sine is that the sine of y equals x. And so, and y equals the sine inverse of x. We're going to use the fact that sine y equals x later, right? And so that's going to come into play. But earlier in the course, right, we said that the inverse sine function, we actually have to decrease it, its domain by quite a bit, and say that, and y is restricted to be between negative pi over 2 and pi over 2. Otherwise, it wasn't 1-to-1, and so we couldn't find the inverse. And so what we said was we were going to restrict the domain to negative pi over 2 and pi over 2, and only look at that section and define that as the domain for the inverse sine. So if we, I'll put it on the next page here. In fact, maybe I should put this whole section, it's not really a new section, but I'll put it on its own page. Make it nice and clean. So if we differentiate sine y equals x implicitly with respect to x. Well, again, right, if we've got sine y equals x, I can take the derivative of both sides. Sine y is implicitly defined in terms of x, and so I have to take, right, we've got another chain rule. Now the wraparound function is sine, and the derivative of sine is cosine, and so we get cos y times the derivative of y, which you could use y prime if you wanted to, times dy dx, or y prime, whichever you prefer at this point. And the derivative of x with respect to x is just 1. So again, solve for dy dx, right, or y prime, whichever you prefer, right? Because now you've seen both and you've probably picked a favorite. Hands up if it's y prime. Yeah. Oh, not sure. Yeah, they're all the same. Yeah. So everyone likes y prime. Yeah, I do too. So then we have, let's just do y prime then. Let's switch it halfway through. You can't do that. I can do whatever I want. Well, not really, but in this case, because they mean the same thing, it doesn't matter. So y prime then is going to be 1 over cos y. So now we need to make sure that cos y is not going to be 0, right? Because that would be bad. Because then we're dividing by 0, which is not allowed. And we're almost out of the woods, so we'll just have to make do, because since y is between negative pi over 2 and pi over 2, right, cos y must be greater than or equal to 0. So 0 is still included there, but we just have to make sure that cos y can't be 0.
So how can it be equal to 0? Because if it can't be 0, then it can't be equal to 0.
If it can't be 0, it can't be equal to 0. I know, so we just have to make sure that whatever y we pick doesn't generate a cos, which would be at the pi over 2, right? Pretty sure.
But would it make sense?
Cos of pi over 2.
Y prime can equal 0, but cos y can't?
Y prime won't equal 0 just because the only way for it to equal 0 is if it's the numerator is 0,
Yeah.
but you can't divide by 0.
So wouldn't that make cos y not equal to 0 then?
Yeah, we have to force it so that cos y can't be 0.
So shouldn't it just be greater than 0?
Yeah, but between negative pi over 2 and pi over 2, it can be, like, it'll just always be positive, but it can also be 0. And I'm pretty sure it's at pi over 2. Let me just make sure here. Pi over 2 is at 0. Exactly. So here, we can't have cos y equal to 0. That's what you mean, right?
Yeah, because you have greater than or equal to.
Yeah. And so, y, therefore y must be less than and not equal to pi over 2. Because it's at pi over 2 that it's going to fall apart. Because that's where cos pi over 2 is 0. Up here.
Wouldn't it make sense if it was y is greater than or equal to 0 instead of cos y? Because I still don't understand, because if cos y is equal to 0, that's still 1 over 0.
Yeah, so that's why we're saying, okay, I'm going to restrict it even further, right? And say that y has to be less than pi over 2 and can't equal pi over 2. Because if it's equal to pi over 2, then I'm dividing by 0, which is bad.
But then if you say that, then it still shouldn't be greater than or equal to 0. Because if it's greater than or equal to 0, then it can be 0.
Right. And so, but what I'm referring to there is that the y is between negative pi over 2 and pi over 2 inclusive, right? And on that interval, cos y is greater than or equal to 0. Right? For all those values between negative pi over 2 and pi over 2 inclusive, all the values of cos y will be positive, but also can include 0. So then what I'm doing is that, well, we're saying we can't have cos y equal to 0. So then I'm going to adjust that top bound to not include pi over 2, because that's where that's going to happen. And so now, right, we would say that y must be less than pi over 2. I am pretty sure it can still be cos of negative pi over 2. It can't be. It's also 0. Just delete it. Because these bounds, the inclusive of negative pi over 2, and pi over 2 is from up here on the sine, right? And so those we're dragging down with us because that's our domain as far as we know. And then now we're saying, I'll just scoot this over, make the adjustment here. Negative pi over 2. Right. And then I guess I don't need this because I did the same thing. So we're just adjusting, so we're decreasing the domain by just a little bit, right? So that we can't include those because then we would be divided by 0. Okay, cos y. If we recall that cos squared y plus sine squared y equals 1, then solving for cos, right, we get cos y must be the square root of 1 minus sine squared y. So we use this trig identity to kind of help us along here. Because what we want to do is we don't just want to leave it in terms of cos y, right? And so here, oh, and maybe that's why it wasn't. Because now that we've expressed it in terms of sine squared, we're back to that original domain. Anyways, doesn't hurt. I'll look into it. So then cos y, we can write as the square root of 1 minus sine squared y. And then here's the trick, is that sine y equals x, right? I'm gonna bring it down, way down here. Oh, a long way to go. Yeah, right, because we said that sine y equals x. So then sine squared y must be x squared. So now we're able to replace this and say that y must be the root of 1 minus x squared. Oh, cos y. I lost it. So now, therefore, dy dx, which we said was 1 over cos y. And now that I think about it, I'll look into it, but that might be the whole reason that we do this. Use this identity is to get it in terms of sine again, so that we don't have more restrictions on y. Anyways, I'll look into it. So the derivative of y, oh, we were using y prime, weren't we? We like that better. Y prime. I'll even say dy dx, which equals y prime, is 1 over cos y, which we can write as y prime must be 1 over the root of 1 minus x squared. we can use similar methods. To find the remaining derivatives of trig functions. Or we can memorize this table, whichever you prefer. And like I said, I'll give it on a printout, but I suspect we'll have a couple more. So you'll just have to wait until we've got a couple more on the printout. But they'll be in the notes for now. So we did the first one. Yeah, sorry.
So you're just using trig identities to put it in terms of that.
Yeah. Mm-hmm. Yeah, and just starting with the fact that sine y equals x, and then same thing, right? Cos y equals x, right? Just by how the inverse trig functions work. So then you'd be able to show all of these, right? We did the first one. This is the one that we did. Done. But you could go through and show the rest using the same methods, right? Just depends on, I wouldn't worry too much about kind of the right-hand side, but definitely the, you know, the usual suspect, sine, cosine, tangent, maybe secant. But that's only two that eliminated. But definitely the left-hand side is going to be go-tos, and then the right-hand side, well, good to know, but and you can find some relationships probably between these. I'm more of a memorizer myself. But any questions? No? More memorizing. Well, that's all I've got for today. So we'll differentiate some logs next day. Just keep at it. Any questions? No? All right. Have a good weekend then. And I'll see you on Tuesday. And you'll get your test back on Tuesday, right? They're marked. Your marks are on Moodle. But there's another class writing a test tomorrow, so that's why you're not getting them back. Cool.